Yeah, welcome everybody. uh, that's the point to pick up your your headphones for whoever is here. Yeah, welcome to our next talk for whomever is here for round two. This time we will talk about Eclipse project Eclipse sensiNact, IoT's next top model, developed as an Eclipse project. More on that later. I'm Jürgen Albert, founder and CEO of Data in Motion. We have more than a decade of experience working with OCI and open source systems. We are active committers to several OCI Eclipse projects. I'm also the chair of the OCI steering committee. We are also having a heavy interest in model-driven development and distributed systems, and also committers on B&D tools and several other OCI projects. Next to me is Tim Ward. Welcome.
So, hello, I'm Tim Ward. I'm CTO at KentU. I've been involved with open source for many more years than I care to remember, but involved with Apache, with Eclipse, with steering committee work for the OSGI working group, various different projects. I've written books about OSGI in the past, and yes, I'm a big believer in open source and the community. So we're here to talk about Eclipse sensiNact, and really what we need to start with is we need to start with talking about the problem. And the problem that we have in IoT is that there are so many things. I just mean, like, the number is ridiculous. Clearly, there are not 18 billion dots on that slide. And if each dot were that many dots, then we still wouldn't be anywhere close. However, if each dot in the second picture were that many dots, then that's still only half of it. You know, this number is really catastrophically huge. And it's therefore actually really hard to appreciate just how many connected devices there are in the world. We think, oh, 18 billion is a number I have a handle on. You really, really don't. I don't know if you ever saw the description of someone who shows like a briefcase of money in a film. And typically, a briefcase full of US dollars, if you use $1 bills, is about 100,000. So you can scale it up by using $100 bills, but we're talking, at most kind of a million or so, really, in a briefcase. If you had a stack of $1 bills, all piled up, just like sheets of paper on top of each other, and you had 1 billion of them, it would be 800 times taller than the Washington Monument in Washington, D.C. It's just 1 billion is an epically huge number. So there is no way that any client we ever make is going to know how to connect to everything that it might come across. It's just not possible. So we need common ways to connect to all of these things, and even like the different types of things. There are within the 18 billion devices, obviously many of them are the same as each other, but there are still so many different classes of device that it is totally impractical to deal with the world. So what we need is we need standards. But the problem is that there are also so many standards. Is it really the case that something is standard when you have so many standards out there? So, and of course, what happens is someone comes along and they say, oh, there are too many standards, I'm going to make my new standard. And then, of course, there is yet another standard. So Eclipse sensiNact tries to not fall into this trap. We do not define a standard, we do not prefer a standard. It's down to you to choose the standards that you want to use, and we will work with that in whatever way we can. So the sensiNact gateway, which is what we're really here to talk about, is at its heart a digital twin. There is a digital twin inside your gateway representing the physical objects in your world with in-memory representations. And the name sensiNact comes from sensing and acting, which is exactly what you can do with this digital twin. You can get or subscribe to data, so you can see the current value of something, or you can see its value changing over time. You can set the values of things, so you can make changes if you had, say, a device which was displaying text, like like at a train station where you have the next train coming and how far away it is. You could set the text that is to display. And then you also have actuations. So actuations would be things like turning on and off a light bulb, opening and closing a lock, maybe even something as sophisticated as opening spill gates for a dam. And all of those things are done through actuation. Now, we have pluggable connectors in sensiNact, and these are what allow us to communicate with all of these devices. So a southbound connector is one that is going to expose devices in the digital twin. So your devices that are outside communicate with your southbound connectors, and as a result, there are devices that appear in the digital twin that you can interact with. You can deploy many of these simultaneously, or sometimes you only need one. Typically, there is a roughly one-to-one mapping between a southbound connector and a protocol, but sometimes you need one per type of device because you have a custom mapping that requires special handling.
Not sure what just happened.
If you're in the situation where you do have custom mapping required, then sometimes you can chain these providers. For example, built into the base of sensiNact, we have a configuration-driven factory for devices where you can supply configuration and then chain that with other southbound connectors to give you suitable parsing for devices that communicate with JSON, with CSV, with XML. Yeah, whatever format it is, it could be a binary format like CBOR, and you can then consume that, chop the data up, and represent it in the digital twin. But it's not just the southbound that's pluggable. It's also possible to be pluggable in the northbound API. The northbound API being the part of the gateway that communicates with the outside world. It's the thing where if you went to your web browser and tried to look at the gateway, you would be talking to the northbound API. And it can use whatever protocol and whatever format you want it to. We have implementations for REST and WebSocket. You can talk MQTT. You can have any serialization format you want. And also, you can adhere to whichever standards you want. So we have existing access layers for OGC sensor things, for W3C web of things, and it's really saying the standard that you use should be the standard you choose, and it shouldn't be determined by the gateway that you run. It should be determined by what makes sense for how you interact with your devices. And that means that the gateway is, in the truest sense, a gateway device. It provides access to your Internet of Things devices, and it provides it in a way that means that you are able to communicate regardless of what is going on in the middle. So one standard up top, you might want to use sensor things to communicate with Web of Things devices. And there really aren't other tools that are capable of doing this. So we have this secret source, which is required. And this is some kind of pluggability that is required. And there are two ways you can look at building plugins. You can either start at the low level and try and build up, or you can start at the high level, defining what you need, and work down. Whichever way you do, you need to define the interface that you're going to use to communicate. And if you've defined that interface you're going to use to communicate, it's then really a case of, is it going to be something that's in process or something that's out of process? Now, these things already exist, right? We're not the first people to think of having a pluggable architecture. So for low-level pluggability in Java, we have Service Loader. It allows us to get an implementation of an interface. It's quick, there's very little overhead, And the dependencies of the thing that we're using as a plugin and the rest of the gateway are shared. If we are, on the other hand, looking at the high level and we want something out of process, then this is where we start talking microservices. We have maybe a container that we start, which is comparatively high overhead. And the benefit we get from that is that all of the dependencies of the plugin are entirely hidden from us because they're inside the container. The problem is with both of these cases that there are, as your need for plugins grows, neither of them are the ideal solution. For low-level plugins, as the complexity of the plugin that you're using increases, the problems you have with deploying it increase too. Every one of their dependencies is also one of your dependencies, and every one of your dependencies is also one of their dependencies. And you spend all of your time trying to work out how to isolate your plugins from one another. You may even end up giving your plugins their own class loader. On the other hand, with your microservices, you end up with an API which is increasingly difficult to maintain the version of, because every single microservice that you're talking to has its own copy of the API, which may or may not stay in sync. Also, if you have many of them, the amount of memory overhead that you have for having all of these plugin instances, typically with their own runtime, their own memory management, their own setup for having a REST endpoint, it becomes hugely wasteful. You can try native memory transports to speed things up and try and reduce some of that overhead, but either way, you're building this huge system. And wouldn't it be great if there was already one that existed? Someone who had this gateway that needed plugins, they needed strong encapsulation of dependencies so there weren't conflicts, and something that could easily be installed. And ideally, if it had as little overhead at runtime as possible, that would be great too. And yeah, OSGI has been doing this for 20 years, right? This is not new. This is exactly why OSGI was created in the first place. And there are powerful development tools, as those of you who were in the previous talk will have seen. And it's something that we can use to build a really powerful plugin architecture for our gateway. So that's talking about Eclipse sensiNact northbound and southbound. We also need to talk about the bit that's in the middle, the sensiNact core runtime. So what is it? Well, ideally, what we have is this universal converter that can convert from anything into anything, and it will all just work. The question is, what is in that box? What is it that we can use to do that? Well, the sensiNact core is really just responsible for managing the digital twin, for having this in-memory representation of the state of your universe. It's going to interoperate between the north and southbound. So we need some way of having flexible data transformation between what we're presented by the southbound connectors and what we're going to expose through the northbound. And as I've said before, we do not want another standard. More standards is not what is needed in IoT. What's needed is better adherence to existing standards and more flexible transformation between them. So we need a generic modeling library that's going to be capable of performing this transformation. Ideally one that's been around for a while, like OSGI, and we know works. And it should have really, really good tooling available. So we want something where we can create this sensiNact model, where we have our providers, which represent the devices, we have the services which group together information, and then we have the resources that provide the individual data values for those providers. So what we want is we want to try and make friends with Eclipse and find out if someone else has maybe solved this problem before.
And indeed, somebody has, also quite some years ago. He's unfortunately not here, because he's sitting next room debugging something. This is basically where we came into the project. We have some experience with that, especially with, EMF. The Eclipse modeling framework is around for like 2002, I believe, the first version came out. Since then, it matured, it is battle hardened, and it's basically the standard way of defining models, at least in the Java world. It has a very small footprint. It has a great performance when you work with it, and it is, as a site, because it is around as long as it has a lot of tooling to define your models, to work with your models, that help you set things up. So because as we don't want to define a new standard, we also don't want to reinvent the wheel everywhere. For example, it is compatible with most of the common UML models, modeling editors. So as shown here, you just see three kinds of representing a standard eCore or EMF model for the whole thing. What is EMF in the end? It is an implementation of the Object Management Group's EMOF standard. EMOF stands for Essential MOF, and MOF stands for Model Object Factory. It's kind of the way you can describe what classes are, what references are, what attributes are, what data types are, things like that. And EMF focuses on the more essential parts. That's why it's called EMOF, the whole thing. It is used to model packages, classes, entities, and their relations with each other. So, and it has a bunch of things that are already kind of predefined. You would in standard UML define yourself, like what is a data type, what is a string, stuff like that is already built in the whole system. We are working with EMF for like more than 10 years as well. So basically at the same time we started with OCI, we started with working with EMF. And there are a bunch of good reasons that became clearer over the years. So one is you have a lot of metadata about the classes and things you work with. So it really nicely describes the structure of your entities, and it is a much broader and richer information set than you would have in Java by inspecting your class, for example. It is supports code generation. By default, it is Java code generation. There are additional things like for TypeScript, for Python. There's also, I believe, for C we found something. So there's a huge ecosystem around it. It also helps you and allows you to link models, so you don't need one really large model, which, if you print it out, would be miles long. You can have small models that are distributed in different places. It also comes with a bunch of serialization formats. So by default, it speaks XML, XMI, or binary. There are additional things that allow you to serialize the things in JSON, in YAML, CSV, you name it. So there's a huge list of additional projects. And not only serialization, it also comes with a form of persistence. So by the default is a file persistence, but it also can be persisted as objects that are EMF objects, can be persisted in NoSQL databases. We have a connector which provides them to Lucene, so you can index these and search these, and soon to be also an SQL or a JPA compatibility layer, so you can persist them in basically any database in the end. But before we go a little bit more into detail, similar to modularity, also modeling is a mindset of its own. So, and why do we need the whole thing? Why do we need modeling? The main reason is we are never alone. We are always part of a bigger system. So, as you have seen on Tim's picture with all the different cables, so you always have touch points with the outside world. Sometimes through standards, sometimes you don't. And this outside world is something we want to interact with, and they want to interact with us. And in order to do so, it is always nice to have a formalized way to describe how you communicate and what you are communicating about. So this neat little picture, you may have seen this somewhere else. You're not always speaking about the same thing, because even language is kind of lacking in that regard. And the other thing is, all these billions of devices send data in a structure. So, and this structure is similar, also not similar, incoming data structure, outgoing data structure. What we hold internally, everything is somehow structured, and we need a way to describe these structures and to avoid, in the end, miscommunication. So that's the general way why modeling is a good thing, not only in our example, but in the general way to describe how you communicate with the outside world. So basically to define your contract with the rest of the world. So EMF, in a nutshell, basically, what you see here is on the left side the definition of how a model could look like. So in this case, you have a package, you have a class. In these classes, you have some attributes. You have another class, and you have references between us, and you can also define methods or operations, it is called, here in that regard. So this is just a representation that lands in the so-called eCore file, which is an XMI or an XML version, basically, of what we have defined there. Then on top of that, for example, you usually have a so-called gen model, which defines how the code generation should work. And these two together result in then some generated code in the end. So over here. Now, the part where, when we think about what Tim showed us before, when we look at EMF and how it can bring something to the table for sensiNact, a digital twin is basically nothing else than a model representation in memory for whatever you have, or in a database, or wherever you want to store it. In our case, it's usually in memory. In this case, models must be somewhat dynamic. This means if new data comes around we haven't heard about before, then this model needs to be extended. So for that, there is a pure Java API you can use in sensiNact, which you could work with sensiNact without having anything to do with EMF in the end. But when you want to have some predefined models because you know what you might expect, then an EMF comes in and is really handy to predefine your models and deploy it via code, for example. But in addition to that, and this is we'll give you a quick glance in the end, you don't need generated code for the whole thing. You also can have them dynamically loaded from somewhere else in a distributed system. So another registry, basically, which knows you want to talk about. Given the picture Tim described briefly, so the overall thing what we have in sensiNact is a model that describes a provider, which is usually a thing somewhere in the real world. As Tim said, you have a grouping of for your actual resources these real world things provide. So, and on the side you see an example from one of our projects where we have such a provider. So you have the model around it, which is the whole package here. In there you have one or more providers if you want. Do I have it correct? Yeah. So that's the provider part over here. In there you have a reference to a service, which is this part here, and the service is defined down here. And in that service again, you have in this case an attribute, which is a resource in that regard. Fun fact is, the nice thing is with EMF, the bug does not stop at the resource level. So when you introspect the sensiNact model, it will tell you until how the resources look like and stuff like that. But you can also put in complex objects, so not only just simple attributes, because sometimes this is necessary. And with EMF, you always know what kind of objects you have there. Not this is just a resource, but this is this concrete object in that regard. But in the end, how do we process data then, and how does this look in the real world? Here we have an example from what we are doing in Jena. They have a bunch of LoRaWAN sensors, and they have this LoRaWAN gateway called ChirpStack in that regard. So where these sensors connect to, and in the end you connect to it via MQTT and get this JSON with a bunch of data in there. When we look at this data, we'll see, as we'll find that there is a common structure. So this is always there. Each device, this comes basically from the gateway. It tells us what kind of device it is, where it is, connection strength, whatever. So some administrative stuff around it. But then you can have different devices there, and each of them send you specific data, which is in this object part here. And this is what we need to take care about and need to somehow structure and work with. So in our example here, this is a moisture sensor for the soil, so it tells you how moist and what the temperature in your soil is. So when we would model the whole thing, this could look like this in the first place. So you see this little thing with the blue corner around it, so this is where the data comes in. Because we don't know what kind of data we get, we just put it in a map. So No, that's not what we want, because a map, when you start like this, a map always means I have no clue what we are having here, and then you can start put everything in maps. So what we actually want is something more like this. So we have a specific device, in this case called the trip stack device, because we don't know what kind of device it is, it just gets a name. We have the general data down here, from which is the comment structure and the comment data, and then we have this data service with the concrete temperature water we find over here for the whole thing. This looks much better, and this is what, when you don't work with EMF, what sensiNact already does underneath. As new data comes in, new attributes are added there, and the model is extended for you with whatever you are coming around. But this is also not really what you want in most cases, because very often you exactly know what you get. In that regard, we know what we will get, and we can structure the whole data. So the actual model looks in the end like that. So we have the general classes. These things are called draginos. These are the name of the sensors, basically. So every dragino looks similar. It has the general device information, which comes from the trip stack gateway. And then we have the sensor itself, which tells us something about its battery status and stuff like that. And underneath that, we have the actual information about the soil. So that's what we want in the end. And then we need a way to get from A to B. From our JSON, we need some kind of a mapping. Tim already talked about this a little bit. Besides, this is what we want. There is a configurable JSON mapping you can give it. So it looks a little bit like this, where I basically say, hey, what comes from here, from that field, please map it in my model on that field. And the model is identified somewhere up here, because this is the identifier for our model, usually an URI. Fun fact is, if sensiNact doesn't know about that model yet, it would look under this URI if it can find it there. So you can also point it to somewhere else, and then it would collect the information from there. The other thing is, we would like to have standardized things to use. And as we said, EMF comes with a broad set of tooling. One of these is, for example, also another Eclipse project, Eclipse QVT. This is what we are using in Jena, which is also an object management group standardized transformation language. QVT stands for Query View Transformation, I believe. And it's another way of transforming the data that is incoming. And something else, so this is what we are working on for the future, having the whole thing a little bit more graphical, that you don't always need a developer for the whole thing. Because that is basically what in the real world you want is not everybody will use this thing and is a developer. So you usually have some people that have a little bit of their domain knowledge, but they can't program, or they don't need to program, or don't want to program, whatever, in that regard. And this is what we currently do in Jena. This is how the urban data platform of Jena currently looks like, or will look like in the future, and you see a lot of boxes here. And sensiNact is just a small part of the whole conglomerate in here. So we are at the point that we have a bigger world we want to communicate with, and in order to do so, we need to know how the data looks like. We receive and also the data we send out. For urban data platforms, it is there are some additional specifications that come with it. One being, for example, that in Germany, the law says that they have to publish the data which is good for the public. So basically, all of it which is not really sensitive to
privacy.
For privacy reasons, thanks heaps. So, and this is what this whole system will do in the end, or can do in the end. In our case, we have this sensiNact attached to the so-called the model atlas, which is also an Eclipse project we are currently developing, or will become an Eclipse project soon. The repository is already under review, and this neatly attaches to sensiNact, where you can store your models and your definitions. So there will be UIs that you can work with, that you can create, where people can create these kind of models and define them in a manner that, like I said, you don't have to be a software developer for the whole thing. And then sensiNact can take these models and say, okay, this is how my sensor looks like. Because somebody with a little bit of domain knowledge can define what this Dragino sensor sends you, what kind of data it sends. And in the long run, the goal is to have all this data available not only to the city of Jena, but also to the rest of the world. So because they need to publish this data, so you need a registry where you describe what kind of data you have, how does this data look like, which formats it have, where the endpoints are, something like that. So it sounds a little bit like a registry. We already have, for example, an OCI. There are a lot of standards and I've missed there's a product called Pivot, so from Fraunhofer, which is used as the data hub for the European Union and also for a lot of the local governments, Germany, for example. And this is a registry where you can find, okay, where can I find my data? So, and what they are all lacking and what everybody needs is how does the data looks like, which is there? Because we don't want to export in the end CSVs or Excel files or whatever, or PDFs. We want hard data we can work with, we can programmatically work with. And this is where EMF comes in again. So we provide basically for everything we do the model definition, and you can get it as a JSON schema, as an XSD if you want it, or as a UML, or as an eCore file in the end. And sensiNact is one part in this bigger system and can interact with the whole thing. If you want to know more about this,
yeah, so you may have noticed one of the different things about this talk is not that you have co-presenters, that does happen, but it's the fact that you have co-presenters here who are from different companies, right? We both work together on sensiNact because it helps us get towards our goals, whether we're coming at it from more of a modeling perspective or more of a distributed systems IoT perspective. And we're using it to solve problems that have been had in Jena, where there are use cases around environment management, around traffic management. Kent, you are using it for utilities management and traffic analysis and long-term trend data. And it's really great that we have this place that we can come together and work on what we need together in a shared tool. And what we need really is we need more of you. We need more of you to be using sensiNact, and ideally, as you become more enthusiastic users, also we want people to help contribute. We want people to help extend, to help grow the sensiNact community. And if you'd like to talk to us more about doing that, then we have a booth over in the area behind us. And please do come and have a conversation. We'll be there for the rest of the day. We'll be there tomorrow. And we'd be really interested to know what it is that you would like sensiNact to do for you, or how you think you might be able to contribute to make sensiNact even better. So you can find us, you can try it out. We have a documentation site with some user examples. You can look at it on GitHub. You can join the mailing list. It's easy to become a committer. The Eclipse Foundation is here. I'm sure that they will welcome you with open arms. And yeah, come and talk to us. Thank you.
Thank you very much.